Now, first of all, today, I was thinking that we might answer this question from the last lecture, which I couldn't think of a good answer for. We were discussing a Galilean coordinate transform from the system K to K prime, or actually, let's see, vice versa. Okay, it doesn't matter much. The transform works the same both ways. Okay, so we say that x in the unprime coordinate system is x prime minus vt, and t is equal to t prime, times the same. Now, we wanted to express the partial derivatives in this coordinate system as, the partial derivatives in this coordinate system, which was the system in which we were considering the wave equation from the start, using the partial derivatives in this system. And then we did an expansion like this, like d dx prime, let x be one of the three x's in k and k prime. Doesn't matter which one, just the one that the velocity is pointing along. Well, now you can write this as dx dx prime d dx plus dt dx prime d dt. Now we differentiate through all the variables that we used in the transform, right? We have x primes and t primes on the right-hand side here. Now this one is equal to 1, and this one is equal to 0. And the question was, why is this 0? Because t is equal to t prime, and then t prime is equal to something that has x's in it. So why is this one 0? And well, a partial derivatives doesn't sort of move on its own, but you could of course use the chain rule, and then proceed to this equation and insert, and then you would get something. But the point is that we want to express the partial derivatives in this system using only partial derivatives from this system. We don't want to mix the two systems. So the suggestion to sort of keep differentiating would actually perform the inverse transform again, and that would bring us back to the system we started in, and that's not very useful. Was that clear? So? Okay. The point is just that if you do that, then you start transforming not in this direction, but you start transforming back again. And if you look at this dt dx prime, well, there's no x prime here. So if you want to find out what dt dx prime is, then you could go through dt prime again using the chain rule. So well, that would be yeah. So it's not useful because then we start moving into the other coordinate system again. So the point is to go from one coordinate system to the other and not to run between them back and forth, because you could do that forever with the chain rule, but it wouldn't be useful. Okay? That's at least the idea. And now for something completely different. Now we're going to continue discussing wave propagation in layered structures. And I'm going to do a small recap of what we saw in the previous lecture. So let's just remind ourselves what the geometry was. It was as follows. You have a substrate at the bottom, which is called medium 2, and it has some epsilon attached to it. Above the substrate we have a thin film. Could be, let's say, 5 micrometers thick, just to take an example number. And on top we have some, this is called the cladding, but we will just set this to air. So let's say we have, for example, glass, like in my glasses, and some thin film, which glasses actually often have on top of it. And then finally we have air. Now we have some, let's see. I need the space, so I'll take that away. So I need the coordinate axis, x3 and x1, like that. This thickness I call d. I have light incident at angle phi naught, like that. And now, let's see, we're going to have a primary reflection here. from the waves being reflected at the top interface of the film. So that's the first reflection. We're also going to have transmission like this. And I define an angle phi 1 in medium 1 and phi 2 in medium 2. And the angles are probably not in the correct proportion, but you get the idea. Now we can also have reflection from this interface, leading to both transmission and reflection here. So we have a second reflection. And you get some reflection back again and transmission here. So we have first and second transmitted fields, and so on for an infinite number of bounces, at least in principle. So these are reflections, and these are the transmissions. Like that. Yeah, so we have some index of refraction, which I'm going to use from now on. In air, it's equal to 1, to a good approximation. In the film, we have some index of refraction which has to be greater than 1. And in the substrate, we also have some index of refraction which is greater than 1. And these are related to the polarizabilities, the permittivities epsilon. You might recall that n in general is equal to epsilon r mu r under the square root. But for most materials that are translucent in the optical region, those materials are usually not magnetic. So we'll just set this guy equal to 1 for today's discussion, just to save some writing. But in principle, it's straightforward to include in the calculation. So it's only the epsilon r that matters for us. OK. Now, there were two things that determined how much reflection and transmission we got. And one of them was the reflection coefficients and transmission coefficients. And the other was the phase difference. Because now you see that if I draw a line parallel to the wavefront here, you see that this ray has only gone this distance L0, while this ray has gone through a distance 2L1. So if I call this length here L1, then this ray has gone through a length 2L1. And because of the index of refraction, the phase has gone a bit further. So the phase difference between reflection n plus 1 and n is given by the following equation, 2 delta. I put the 2 there because of some practical reason, which will be apparent shortly. That's the total phase difference. It's equal to 2 k1 L1. That's this path here, minus k0 L0. That's this path length here. OK? And now, just to remind you, k1 is equal to 2 pi over lambda 1, or 2 pi over lambda 0, the vacuum wavelength, times the index of refraction n1. So it's some constant here, and the index of refraction, which depends on the material. And to find these lengths, that's simply a trigonometric exercise. So I leave that for homework if you're really interested. It's also in the compendium on this topic that I put on the homepage, so you should be able to find it there. And in the end, delta can be shown to be 2 pi over lambda naught n1 d cos phi naught. So phi naught is the angle of incidence, n1 the refractive index of the film, and this is a constant, which is the vacuum wave number. So that's not too hard to show.
Okay.
Yep.
Why is 2 before the delta, in front of the delta?
I choose it because it's convenient. I could just skip the 2 and then have a different delta. Then this would be delta halves. But there's going to be some practical...
Den delta ikke det fastkjøpsmørk?
2 delta is the phase shift.
Okay, okay.
Yeah.
Thank you.
Right. Thanks for clearing that up. Okay. And in the following, we considered the Senkrich polarization, which was that the E field was polarized into the plane, like this. And when we say polarization, we always think about the E field. Okay? And this is because then the boundary conditions are particularly simple. But you can do the same thing with parallel polarization, except then you work with that component of the magnetic field instead. Anyway, it doesn't really matter which polarization you use in the formula we'll find in the end. Now, let's see. The E field in region 0, that's the region the light is reflected back into for Senkrich polarization, is parallel to x2, and it's simply E to I k r. That's the incoming. Incoming light coming in at wave vector k. And then there's the first reflection, which is R01. That's the Fresnel reflection coefficient, which we found before by matching the boundary conditions. It's the Fresnel reflection coefficient coming from medium 0, going into medium 1, but being reflected back out into medium 0. So that's R01, and E to I Q naught, R naught. And Q naught, that's simply the wave vector coming out here. So it's the same length as K, and the angle is conserved, right? So this is also phi 0. Same as always. When you have a reflection at the planar interface, the angle of incidence is the same as the angle of reflection. Okay, the next reflection we found to be equal to T01. That's being transmitted from medium 0 into medium 1. And then R12, which is being reflected at the bottom of the film, coming from medium 1, going into medium 2. And then again being transmitted coming from medium 1, going into medium 0. That is, we have transmission, reflection, transmission. Okay? And here we see that we have E to I Q naught, R naught here as well. But also we have a phase factor, E to 2I delta. And then there are going to be higher order reflections, which are going to follow the same pattern. So if you look at the third reflection, then it's going to have an extra reflection, reflection, right? Because we have transmission, reflection, transmission. But now we move that transmission here, and we have an extra 2 reflections. Meaning that I can write this as an infinite sum. So that's first and second reflection. And I can write that as an infinite sum. So the total R, which is the total Fresnel reflection coefficient for a thin film on top of a substrate, is equal to R01. That's this reflection off the top. And plus T01 R12 T10 E to 2I delta. And now an infinite sum. N is equal to 0 to infinity. And we have E to 2I delta to power n, R10, R12 to power n. This looks a bit terrifying at first, but fortunately it's just a geometric series, so I can easily sum it using a standard formula. So the total reflection coefficient is R01, T01, R12, T10, E to 2I delta. That was a bit tight. And 1 minus E to 2I delta, R10, R12. Okay, so this is this term here. That's the Fresnel for a big slab of the same material as the film. And this is the interference effects from the bouncing inside the film. So this is the let's see, this is d small effect. Because the thickness of the film is small compared to the wavelength, or at least not so much bigger than the wavelength. And well, the reason I can write it like this is, of course, that this exponential here is the same for each term. They just add an extra phase when I have higher order reflections. So that's what we found last time. Was this clear? Yeah? Okay, so now I have a question for you to discuss with your neighbor. Since we have a plus sign here, is the reflection from a substrate with a film always higher than the reflection from a material made of only the film material? Do you understand the question? So if I would only have this material going down to minus infinity, there would just be this reflection, right? But now if I add all this stuff, does that always enhance the reflection? And more importantly, why? So discuss with your neighbors, and you have 2 minutes. So, has anyone reached a conclusion? Right, so the answer is that e to 2I delta can be any complex phase, so this could be any complex number, and hence you could get either a positive, negative, or complex contribution to the reflection. And that's correct. There's a small refinement to your answer, and that is that R and T can, in general, be both positive and negative. And even more generally, if you have conductivity in the material, you can also have a complex phase on these numbers. So R and T can in general be complex. So if you go back to the Fresnel formulas and have a look at those, you'll see that, well, because of the sign here, you could, even if the e to 2I delta happened to be +1, for example, then even that could give you a negative contribution. But yep, that's a good observation. A note here that, well, yeah, I think that was it. So everyone got that? Great. And now we can find the transmission in a completely analogous way. So, if I want to find the total transmission, I proceed completely analogously, writing that the total transmission amplitude, well, that will be equal to, first of all, T01, and then some phase, and then T12. So it should be T01, T12, and then a phase, e to I delta. And again, you'll have to do the calculation and look at this length L2. But it might, I mean, it turns out that the delta is in fact the same as here. This is perhaps not so surprising if you consider that for one of these bounces, it takes the same amount of time. So omega t wise, it takes the same phase to do one bounce. So for that reason, I think it's not so surprising that the delta turns out to be the same. But if you want to convince yourself, you'll have to compare this phase here as well. The higher order term, next one is going to be T01, T12. And then we have two extra reflections, right, from the bottom and the top. So that's R12, R10. And we have e to I3 delta, because now we made 3 traversals through the film. So it's 1, 2, 3 deltas. And the higher order terms, Well, they proceed in the same fashion, adding an extra factor R12, R10 because of the extra bounds, and an extra factor E to I2 delta. So as before, we get E to I2 delta from an extra phase, but we also get a phase from the first traversal of the film. And this gives us, in a similar fashion, let's see, T01, T12, E to I delta, and more or less the same sum, R12, R10, E to 2I delta to power n, where n runs from 0 to infinity. And because this is, again, simply a geometric series that should converge, otherwise we'd have some sort of energy source, meaning that I can simply write down the answer, T10, T12, E to I delta. That's the prefactor. And here I get 1 minus R12, R10, E to 2I delta. Okay. And I would like to stress that R and T, they connect the field amplitudes. This is important, it's not the intensities. This is also why you get this complex phase, because when we write the electric field as some sort of E to I, Kx, and so on, then it has a complex phase in general, right? So if I want to find out how the electric field on top of the film relates to the electric field below the film, I will need to consider the phase if I'm going to have the whole truth. But in the end, you often measure the intensities, and then you can calculate the intensities in the same fashion as we did for a single interface. And that gives us, for example, that R, that was equal to, let's see, R absolute value square, right? So the intensity is related to the reflection amplitude. And for the transmission, there was an extra geometric factor, but you can go back and have a look in the book if you want to see those details. Okay? So now we got the same as we did for a single interface. We got a reflection amplitude and a transmission amplitude, and from that we can calculate intensities if you want. So, was that okay for a single film? And then I think we can move on to multiple films. So, we now know the truth about a single film on top of a substrate, but what if you have two films? So if I have some substrate, first I put a film 1, and then I put a film 2, and then we have air. And now you'll see that the picture becomes increasingly complex because we have multiple reflections all over the place and multiple transmissions. So how the hell do we make any sense of this stuff? And in fact, it's not so hard, because we know the reflection coefficient for a single film. And if we now in that film, in let's say film 2, we can replace this reflection coefficient here by the reflection coefficient from a film on a substrate. So we can use the old formula to recursively extend our formula for many films. So we can just, as long as we found for one film, you can just build it up for as many films as you like. In principle, this is straightforward. In practice, this gives big and nasty expressions, as you might have guessed, because you'll get for each reflection coefficient between films, you will get a big and nasty factor like the one I just wrote up. So let's have a look at that. If you recall now that R is equal to R01, that's the top reflection, plus all the bouncing inside film 2. So let's see, I still call this medium 0, 1, 2, 3, confusingly. So the reflection coefficient will be R12, T01, T10, e to 2I delta over 1 plus R12, R0, e to 2I delta. Now you'll see that this R12, I can replace that with the reflection coefficient from this film. Right? And what does that mean? That means that inside this factor and this factor, I will get an expression that looks like this, except it will have R12, R23, T12, and so on. Yeah? It's a minus sign, like the lady says. Okay, so for each of these factors, we get an expression like this, meaning that this quickly explodes if you have, let's say, 3 or 4 films. It's completely intractable. But in principle, it's straightforward. So you can do it if you like big expressions. Now, there was a clever guy who invented a more convenient approach to this, and it's called the transfer matrix technique. And transfer matrices is not confined to this simple problem here. It's a general mathematical technique which is used in several, let's say, engineering and science disciplines. So that's a mathematical technique. It's the idea of transfer matrices is simply to relate physical quantities at one point so we relate physical quantities at one point, let's say point A, to the same physical quantities at point B by a matrix multiplication. And this might seem like something that's relatively uninteresting, but let's say I have a vector of quantities here at point A, and if I can relate those to, well, I have some system here, let's say thin films, then I can relate those to the quantities at point B by a matrix multiplication. Now this, as I said, this is not interesting in itself, but what if I wanted to relate them at point C and point D later? Well, then I just multiply another matrix which represents the system for each point I'm moving through, okay? And this is applied in several fields of science. So example applications. They might be thin films. And also geometric optics. So if you think about, for example, your camera, it has curved surfaces, and then it has a piece of glass, and then it has a curved surface, and so on. If I want to relate the light coming into the camera to the light hitting the film or the electronic chip these days, then I just put I could just put a matrix for each physical element through there. In the same way, I can give a matrix for each thin film. It's also used in accelerator optics. So when someone wants to calculate the beam properties inside the LHC, for example, they do a lot of matrix algebra, and then you can calculate the optics properties around the accelerator simply by starting at some point, multiplying a bunch of matrices to get to the next point, one matrix per physical component. Yeah, and then you get the answer quite easily. And as you might have guessed, computers are really good at multiplying matrices, but they're not good at handling big analytical expressions, meaning that you can quite easily analyze a very large system, like a many kilometer long particle accelerator, or let's say a camera with 10 lenses. Try doing that by hand, you'll go nuts. And well, if you do this with 3 films, I think that's enough to demonstrate the point that this is very hard to do analytically.